Alright, physicists, so we're going to talk about a mechanical wave. So a mechanical wave is what we get when energy moves through matter. So if we talk about electromagnetic waves, that can move through a vacuum, but right now we're going to stick with mechanical waves, and they work by vibrating. So mechanical basically means to move, physically move. So it works by vibrating particles. So you get a mechanical transfer of energy, which means, as it says here, one particle bumps into the next particle and transfers energy. So see, it bumps, and he's got lots of energy, and now some of that energy is going back into this guy, and here those particles are now bouncing off in that direction, whereas these ones start to come backwards. So you get that kind of emotion. So particles that move by bumping into one another, those are mechanical waves. Now, two examples are waves in water, okay, and that's a transverse wave, so that's this one. And the other one are sound waves. Now that's a longitudinal wave, as it goes this way, and because the particles compress, and you should write this down as well, because the particles compress, it's also called a compression wave. So on that in particular, we have sound waves. So again, they're a mechanical wave, usually in air, but you can hear sound in water. And if you put your head against a table and you tap on it, you'll hear the sound through the table. It should also say up there, it needs particles, okay? Sound won't travel in a vacuum. So vibrations move the air particles. Now if we have speakers, they move in and out. We'll show you down here. So you've got an electromagnet that turns on and off. You've got a bit of metal at the end and the paper cone, and that causes the paper cone to move in and out. So that causes the air to vibrate, and that's why they move really fast or slow, depending on what it is that what sort of sound they're trying to make. So air particles then bump into the particles next to it, and the bumps into the particles next to it, and so on, and we get it to move. And we get a wave that looks like this. Alright, now, we can still draw it as the traditional transverse wave to show you what it looks like, but it actually looks like this bottom one here. So this is a reference point to show you. It's what we call a reference wave, and this is to show you what it actually looks like. So all the little dots are air particles, and you can see that they compress in and expand out and compress in, and that's when they're doing these ones. So here these particles are compressed in, and then they're going to expand, and they'll bump back into these ones, which will then expand out. So where they're in nice and tight, that's a compression zone, and where they're spread far apart, that's rarefaction. So that's a rarefaction zone. So we've got rarefaction, compression. Here we can see where the amplitude is at its highest or lowest, so crests and troughs. We can see that's what it looks like when it's most intense, because that's where the intensity comes from. And we can even measure the wavelength along that. That's sound waves. Alright, so that'll do for today, and yeah, we'll see you in class.